Hello everyone, welcome to week 10 of another communication problem solving session. So today we will be solving problems on the frequency modulation. So today's problems will be on FM modulation. So as we solve these problems, also we will also go through we will also go through the basic concepts of this presentation. So here the first question is that in frequency modulation, that frequency deviation is directly proportional to A, amplitude of carrier signal, B, frequency of carrier signal, C, amplitude of modulating signal, D, frequency of modulating signal. So here you have four options. So there are two signals, carrier signal and modulating signal, and the frequency deviation of an FM wave depends on the signal, which depends on which quantity of which signal, amplitude or frequency of carrier or modulating signal. So we will look into that. What we will do is we will write the expression for frequency modulation. So there is a carrier. First there is a carrier. Carrier is defined as AC cos 2 pi fc2, and then there is a modulating signal which is given as AM cos 2 pi fm. Now in frequency modulation, the frequency of the carrier is modulated according to the message signal. Frequency of carrier is modulated according to the carrier, according to the modulating according to the modulating signal. So here the amplitude of the carrier, in the modulated wave, the amplitude will be simply equal to the amplitude of the carrier. So there is no change in the amplitude. So the modulated wave will be AC. Amplitude will be AC. Cos 2 pi. Now this frequency will no longer be FC. Instead it will be FC plus delta F T, where delta F is equal to some constant beta times Am cos 2 pi F. So the frequency deviation depends on the message signal. So frequency deviation depends on the amplitude of the model. Now if you take the magnitude of this modulation, max, so maximum frequency modulation. So what will be max? Max will be beta times A, because maximum value of cos is 1. So the frequency deviation is directly proportional to the amplitude of the modulating signal, and whose peak value is beta times the peak value of the carrier signal. This beta is a conversion constant or proportionality constant. So this is beta is called the modulating index of FM. This beta so this beta is the modulation index or the depth of modulation of FM. So this beta value signifies how much the signal has been modulated. What is the degree of modulation of the signal? Now, so the first question answer is amplitude of the modulating signal. The frequency or deviation is directly proportional to the amplitude of the modulating signal. Amplitude of the amplitude of the modulating signal. Next, a frequency modulated signal can be demodulated using a multiplying with carrier frequency followed by low pass filtering, passing through a voltage control oscillator, passing through a differentiator, and passing through an integrator followed by envelope function. Now, the first option, multiplying with carrier frequency followed by low pass filtering. This is the classic amplitude demodulation. So this one is not actually frequency modulation. This is the classic amplitude demodulation. A VCO or voltage controlled oscillator, it generates a voltage or tone that is proportional to the frequency. So it generates it generates a tone that is proportional to the voltage. So here the also frequency of the tone in a VCO is controlled by the input voltage. So this can be a viable candidate for frequency modulation. And another is passing through a differentiator or passing through an integrator, followed by envelope detection. Now, now there are two viable options. One is passing through a voltage control oscillator, and another is passing through a differentiator or an integrator. So for the clarification of that, though for between these two options, we have to look at the architecture of a FM demodulator. So if you look into the FM demodulator, you will see there are two types of these. One is using the voltage controlled oscillator, and another is using this calculus differentiator integrator. So what is given here is that the equation for FM is this. Okay, So here the frequency is a derivative. Now we know that frequency is the derivative of phase. So if you differentiate phase with respect to time, you get frequency. So if you integrate frequency with respect to time, you will get phase. So integration mtdt is basically the phase of the FM wave. Now if you differentiate, with respect to t, then you will have something like a sinusoid and an amplitude that is proportional to the message signal. So we can say that we can detect this message signal directly from the amplitude. So if we differentiate the FM signal, we will get something like this: 2 pi a AC into 2 pi a FC plus 2 pi kf mt, where kf is a proportionality constant like beta. So we can say see that the amplitude of the derivative is directly proportional to the message signal. So if we can isolate this amplitude of the derivative, we can get the message signal. So one way of demodulating is you differentiate and then you differentiate and you then isolate the amplitude, which is done by envelope detection. So here you can see ST, as we have written, is AC cos 2 pi FCT plus KF into integration MT dt. 2 pi FCT plus 2 pi KF integration MT. Now, if you derive this with respect to time, now if you derive this with respect to time, you will get AC 2 pi FC plus the integration MTDT, the derivative of integration MTDT, you will get just MT. So it is 2 pi KF MT. So, and you get cos ka derivative minus sine. So sine something, it doesn't matter. Sine. So the envelope only matters here. So this part, you pass through an envelope detector and you will get something like AC 2 pi FC and plus DC blocker. Let's say plus DC blocker. Then you will have 2 pi. This part will get eliminated by the DC blocker 2 pi FCAC. So you will have 2 pi KFAC empty. So it is in one way, if you just ignore the constants, it is just decoding the message. So differentiator followed by amplitude modulator is one way of solving this. And another way of solving this demodulation problem is using voltage controlled oscillators. This method is called the phase discrimination method. In this phase discrimination method, what you do is you pass the signal through a low pass filter, and basically you pass it through a voltage control oscillator, and then you pass it through a low pass filter. So this way, whatever the FM wave amplitude is there, corresponding frequency will be generated, and with respect to that frequency, we will carry out the demodulation. So we are getting, in a way, since VCO can generate a specific tone with respect to voltage, we are in a way generating the voltage, generating the frequency back. So it is another method. So here, just passing through a voltage controlled oscillator. Now option B is a valid option, but it is incomplete, because just passing through, this is incomplete, because just passing through a voltage controlled oscillator won't give you any result. You have to create a feedback loop. You have to create a feedback loop of the voltage control oscillator and a low pass filter to generate the FMD modulator. So the only correct option here, fully complete correct option, is option C. So correct answer is C, passing through a differentiator followed by envelope detection. Now in question 3, a block diagram of Armstrong FM transmitter. So in Armstrong FM transmitter, you basically create a small narrowband FM, and then you multiply that narrowband FM with frequencies to create, with higher frequencies, to create a wideband FM. So an Armstrong FM transmitter does not create FM, it widens the bandwidth of FM. So here you have a message signal MT, which is passing through a narrowband frequency modulator, or NBFM, followed by a frequency multiplier which multiplies the frequency n1 times, and then you have another frequency multiplier which comes after a combination with the local oscillator, and that will multiply the incoming frequency by n2. So n1 and n2 are given to be 64 and 48, and f1 is 200 kilohertz, and FLO is 10.8 megahertz. So the center frequency of the signal obtained at the output of the local oscillator. So the output here, xt, we have to find the center frequency of the signal. The center frequency of the incoming signal, incoming narrowband FM, is given as f1. So f1 is 200 kilohertz. That is given. So after this, here, what will be the frequency? It will n1 be n1 f1. So here it will be n1 f1. Now n1 f1 is getting combined with a FLO. So here the frequency, let's name this point as A, this point as B. So FA is n1 f1, and FB is n1 f1 plus FLO. Now the final output frequency f0 is n2 fp. So it is n1 n2 f1 plus FLO. So here we have n1 n2 n1 into n2 f n1 into n2 f1 plus flo or minus flo plus n2 flo rather plus n2 flo plus minus n2 flo. So first we have to calculate n1 into f1. So n1 into f1 is 64 into 48 into 200 kilohertz. So it is 64 48 into 200 kilohertz. So 0.2 megahertz. 64 into 48 into 0.2, 614.4. So N1 into F1 is 600 614.4 and into FLO. So FLO is 10.8 megahertz. So into FLO is 48 into 10.8. 48 into 518.4. 518.4. So here 614.4 plus 518.4 is 1132.8. So one center frequency will be 1132.8 and another is 614.4 minus 518.96. So another is 96 megahertz. One is 1 1132.8 and another is 96. So correct answer is option B. The center frequency at the output for Q3. So here the center frequency at the FLO and the center frequency at the Q3 as output is given. So because this is a हेलो हाँ हाँ बोल हाँ बोलिए अरे भाई थोड़ा टाइम तो दीजिए आप लोग दिन में 4 बार कॉल करते हैं एक दिन में बाप रे बाप हाँ हाँ ठीक है, ठीक है, ठीक है, ठीक है। हाँ। उफ, चलो कॉलेज। So here this is a frequency multiplier. So what a frequency multiplier does in effect is, if you have a band like this, if you put it through a multiplier, it will not shift your frequency, it will just increase the bandwidth. So whatever the bandwidth was before your frequency multiplier, your bandwidth after frequency multiplier will be same. So the center frequency, sorry, the bandwidth will multiply, but whatever the center frequency is at the B will also be at the output of frequency multiplier. So the frequency multiplier itself does not change the center frequency. So here also the correct answer will be 1132.8 and 96. In FM, if the frequency deviation is increased while keeping the modulating frequency constant, what happens to the band? So in FM, there is something called a Carson's rule. Carson's rule, which states that the bandwidth of FM is directly proportional to the frequency definition. So the bandwidth of the FM is directly proportional to the frequency definition. This is Carson's rule. So here what they are saying is that keeping the modulating frequency constant, the frequency deviation is increased. And how is that done? Delta F equal to beta beta AC cos beta AM cos 2 pi FMT. So this is your frequency deviation, beta AM cos 2 pi FMT. Now here you are saying that this beta is a proportionality constant, so you cannot change that, and we are saying that this is also held constant. So what you do is you just increase the amplitude of the message signal. That is the only way you can increase the frequency deviation. But if you do increase the frequency deviation, the bandwidth will be directly proportional to the increase in the frequency deviation. So this is known as the Carson's rule. So if the bandwidth or if the frequency deviation of an FM is increased, the bandwidth will also increase. Now question 6. There is a message signal MT which is shown below. Okay, so a message signal MT is a trapezium. So it goes up till 2 seconds, then it stays constant for 1 second, and then it goes down for another 2 seconds. So here this MT is phase modulated on a carrier with the on the yeah. So here we are talking about phase modulation. So we have talked about frequency modulation. Phase modulation is kind of related to it, not very different from frequency modulation. So Now in phase modulation, you have something like a carrier signal whose amplitude again remains unchanged. But instead of expressing the frequency as a function of the modulating signal, we will express the phase as a function of modulating signal. So generally you have AC cos 2 pi fct plus phi. So this phi will be a function of the message signal. So it is AC cos 2 pi fct plus k into kp rather into mt, 2 pi to make it an angle. So 2 pi kpmt. So this is a phase modulator. Now, if you want to convert this into a frequency modulated signal, what you have to do is instead of mt, since this is the phase, now if you want to express this in terms of frequency, frequency is nothing but the rate of change of phase. So the frequency deviation will be nothing but 1 by 2 pi d phi dt. So it is 1 by 2 pi kp 2 pi dmt dt. So the frequency deviation of this PM phase modulated wave is kpm dot. So if you use mt instead of m dot t, so if you use rather m dot t instead of mt, you will land up with fm. Similarly, if you have mt as your fm, then the integration of mt will give you phase modulation. So to summarize, so in summary, if you want to have phase modulation which has a message signal mt, you differentiate that and you will get m dot t, which gives you frequency modulation. Similarly, if you have frequency modulation with a message signal mt, just integrate that and that will give you integration mt dt, which is a phase modulation. So this is the relation between phase modulation and frequency modulation. Now here the message, here there is a phase modulation. So 100 cos 2 pi into 10 to the power 60, that is phase modulated with the trapezium shown, and that it is phase modulated with the trapezium. So we will write the expression for the phase modulation. So phi is given as kp mt. So this is the phase deviation. So total phase is given as 2 pi fc t plus 2 pi kpmt. Now 2 pi kp is given to be 3 radians per volt. So this constant is 3. So it is 3mt. Now this is 2 pi into 10 to the power 6 into t. So the phase deviation is 3mt. So the max phase deviation, which is what is needed in this question, the max phase deviation, max delta phi, is nothing but 3 times the max of mt. Now what is the max of mt? As we can see from this graph, that mt increases from 0, reaches till 20, then stays at 20 for 1 second, and then it falls down to 0 again. So 20 volts is the maximum value of mt. So the maximum value of phase deviation will just be 3 times that. So 3 into 20, that is 60 radians. 60 radians will be the maximum phase deviation. Now they are saying what is the maximum instantaneous frequency. So the maximum instantaneous frequency, first we need to find the instantaneous frequency and then we can maximize that. So the instantaneous frequency is given as the differentiation of the instantaneous phase. The instantaneous phase is given as 2 pi into 10 to the power 60 plus 3 mt. 2 pi so the maximum instantaneous phase is given, maximum instantaneous frequency is given by 1 by 2 pi times this d phi dt. The instantaneous frequency is 1 by 2 pi d phi dt. So it is 10 to the power 6 plus 3 by 2 pi mt. 3 by 2 pi, sorry, m dot t. Now, what is the value of m dot t? M dot t is nothing but the derivative. So here, in this portion, if we plot the m dot t, let's draw the m dot t side by side. So when it is rising with a gradient of, it reaches 20 in 2 seconds. So it is reaching at a gradient of 10 volts per second. So d phi dt is 10 volts per second. Then it becomes flat, so the gradient sharply falls off to 0. Stays in 0 for a while, then it goes to, the gradient now falls off in 2 seconds with the same rate, minus 20. So now the gradient is like this. So this is 20 by 2, so 10. And this is 20 by 2, so this is also 10 but minus. So, and this is 0. The maximum instantaneous frequency will be the maximum value of this. So f max is 10 to the power 6 plus 3 by 2 pi. And what is the maximum value? The maximum value of the gradient is 10. As is shown here, the maximum value of the gradient is 10. This value is the maximum. So it is into 10. So 10 to the power 6 plus 15 by 5, or 30 by 2 pi. The option B, 10 to the power 6 plus 30 by 2 pi. আসলে এইভাবে বসলে না ঠিকঠাক করে টেবিল চেয়ার তো আছে, টেবিল কোথায়, তো জিনিস খালি করা যাবে। ওইটাকে বের করে নিয়ে বুঝতে পারিস। Okay, so for the next question, a single sideband modulation can be viewed as a hybrid form of amplitude and frequency modulation. The envelope of an SSB wave, the envelope of an SSB wave is so uh, so here m hat t, as you can see there is mt and there is m hat t. Mt is the message signal as we all know, and m hat t is the Hilbert transform of the message signal. So the Hilbert M hat T is the Hilbert transform, that is negative pi by 2 phase shifted version of MT. So we have to find the envelope. The envelope options are mod MT plus M hat T, mod MT minus M hat T, and the Pythagorean sum of MT and M hat T, or none of these. So the envelope of an SSB is given as ST equal to MT cos 2 pi FCT plus minus m hat t, which is the Hilbert transform of mt, sine 2 pi fct, sine 2 pi fct. So here you have this signal. Now what is asked is the envelope. Now regardless of what the value of mt and m hat t is, the envelope of a cos b plus b sine, a cos theta plus b sine theta, the envelope is the Pythagorean sum of a and b, that is root a square plus b square. This is universal regardless of the value of mt, fc doesn't matter. So it is root mt square plus m hat t square. Now if this is the envelope, then that is the answer. So yeah, nothing much more. So the correct answer is the Pythagorean sum of mt and the Hilbert transform of mt. So root under m hat mt square plus m hat t square. Now, what is the instantaneous frequency for the lower sideband transmission for the same SSB modulated signal? So the question is that for the same SSB modulated signal, what is the instantaneous lower sideband transmission? Now we have to find, we have to express this as a single cos term, and only then we can have an instantaneous frequency. So that is given as theta it equal to 2 pi fct plus tan inverse minus m hat t by mt. So the derivation you can find in any textbook about single sideband modulation. So the phase is given as phase of SSB and for lower upper sideband it will be 2 pi fct minus tan inverse. So here it is theta it is equal to 2 pi fct plus tan inverse minus m hat t by mt. Now the instantaneous frequency is d theta d dt. So into 1 by 2 to normalize the things. So the first term will just give fc, and the second term is the differentiation of tan inverse. The differentiation of tan inverse gives 1 by 1 plus m square t by m hat t square. So here let's do this on the board. So here we have instantaneous frequency as 1 by 2 pi d dt of tan inverse minus m hat t by mt minus m hat t by mt. This is the instantaneous frequency ft. Now this can be simplified as tan inverse x. The derivative of tan inverse x is 1 by 1 plus x square. So here it will be 1 by 1 plus m square hat t by m square t. And another part will be the derivative of this fraction. So the derivative of fraction is given as m square square of the denominator mt m hat dash t minus m dash t m hat. So here the m square t will cancel, so it will be 1 by 2 pi 1 by m square t plus m hat square t. This m square t will cancel with this m square t, and you have on the numerator mt m dash hat t minus m dash t m hat t. So this is the final answer. Here we can see all of them are m hat t m dash t plus mt m hat dash t, or some iterations there. But we need a subtraction sign in the middle, so none of these options are valid. The correct answer is none of these. Now it said that consider a wideband phase modulated signal by produced by sinusoidal signal modulating wave am equal to cos 2 pi fft using a modulator with phase sensitivity equal to kp. So there is a wideband phase modulated signal which is produced by a modulating wave am cos 2 pi fft, and It is produced using a modulator whose modulation index or phase sensitivity, that is radian per volt, is kp. Now, if the maximum phase deviation is large compared to 1 radian, the bandwidth of the PM signal can be approximated as. So, bandwidth will be directly proportional to the frequency deviation. So, whatever the frequency deviation is, we can just put something proportional to that. But the frequency deviation will be a kp into fmam, because kp into fm, kp is the phase deviation, and let's do the derivation rather. So it is the instantaneous phase of a phase modulated signal is given as theta t equal to 2 pi fc t plus kp into mt, which means it is 2 pi fc t plus kp a cos 2 pi fmt. So the ft is given as 2 pi fc, so it is theta dot t, which will give 2 pi fc minus kp a sine 2 pi fmt. So the maximum frequency deviation delta f is kpam into 2 pi. Okay, there will be 2 pi from outside. So sorry, here I have done a small mistake. So the 2 pi fc minus kp into 2 pi am fm sine 2 pi fmt. So delta f max, the maximum frequency deviation, will be by 2 pi. So if you have to divide by 2 pi, you will get maximum frequency deviation as kp am fm. So this is the maximum frequency deviation. So the bandwidth b will be 2 into fm plus delta f. This is Carson's rule. By Carson's rule, by Carson's rule. Bandwidth is 2 into delta f plus alpha. So it will be 2 into kp am fm plus fm, which is 2 fm kp am plus 1. Now it is given that the maximum phase deviation, that is kp am, is much greater than 1. So it is given that kp am is much greater than 1. So if kp am is much greater than 1, then bandwidth is 2 pi fm kpa. So we can ignore that one. 2 pi fm, sorry, not 2 pi, 2 fm kpa. So the final answer is 2 fm kpa, option B. So that brings us to the end of the regular assignments. So now we will take on some extra problems for you to be examining in 1 minute. So next we will be looking at some we will be looking at some frequency modulation signals. If Vt equal to 20 sine 2 into 10 to the power 8 phi t plus 10 sine 500 phi t represents FM signal, then modulating signal and maximum frequency deviation is dash and dash. So there is a FM signal which is given as 20 sine 2 into 10 to the power 8 pi t plus 10 sine 500 pi t. So as you can guess, 2 into 10 to the power 8 pi t. So 10 to the power 8 is the carrier frequency. So it is 0.1 gigahertz or 100 megahertz. Next, there is a message signal 10 sine 500 pi t. Now, the modulating signal frequency and maximum frequency deviation. So modulating signal frequency means FM and maximum frequency deviation is delta F. So we have our signal. So FM signal is given as Vt equal to 20 sine 2 into 10 to the power 8 pi t. Vt equal to 20 sine 2 into the power 8 pi t. Next is the 10 sine 500 pi t. This is the phase. So next we have to find the signal frequency, the modulating frequency and maximum frequency deviation. So here usually what is given is AC sine 2 pi FCT plus KPAM sine 2 pi FMT. So this is the FM signal. So if we compare 1 by 1 is to 1, we get AC is equal to 20, FC is equal to 10 to the power 8 or 100 megahertz. Next, KPAM is equal to 10, and FM is equal to 500. Sorry, 250 hertz. FM is equal to 250 hertz because 2 pi FM is 500 hertz. So FM is 250 hertz. So the modulating frequency is 250 hertz. Now, what is the instantaneous frequency? So the instantaneous phase deviation delta phi is given as kPan sine 2 pi fmt. So delta f is 1 by 2 pi delta phi delta t. So this will give 1 by 2 pi kPa cos 2 pi fmt into 2 pi fm. So 2 pi gets cancelled. So it becomes kPamfm cos 2 pi fmt. So delta f max. So what is the maximum frequency deviation? It will be when cos is 1, so that is kPam fm. This will be the maximum frequency deviation. Now, as we have compared, kPam is 10, so it is 10 into 250. So it is 2500 hertz or 2.5 kilohertz. So 250 hertz and 2.5 kilohertz. So correct answer is option 3. Correct answer is option 3. Next. Which of the following statements which of the following statements is true for which of the following statements is true for FM or frequency modulation? In FM, amplitude is constant but phase varies, which is correct. And next is in FM, both amplitude and phase vary, which is wrong. And in another, it says in FM, amplitude varies but phase remains constant. Again, wrong. This is amplitude modulation, so not frequency modulation. And next, in option 4, in FM, frequency varies and amplitude and phase remain constant. Now, frequency is the simple derivative of the phase. So, if the frequency remains variable, the phase has to remain variable. They are interlocked together. They are not independent variables. So, the correct answer is option 2. In FM, both amplitude and phase vary, but frequency. Sorry, option 1. In FM, amplitude is constant, but phase varies. So, and by if phase varies, then frequency will also vary. So, correct answer is option 1. Here it's clear wrong. The solution is wrong because if frequency varies, the phase has to vary. You cannot have frequency variation without phase variation. Next, a wave has three parameters: amplitude, phase, and frequency. There are three types of modulation techniques. One is frequency modulation and amplitude modulation and phase modulation. Okay. So a PLL can be used to operate one, two. So yeah, a PLL can be used to demodulate DSBSC signals, FM signals. So PLL generates tone corresponding to input voltage. So whatever the voltage is coming, we have to generate a frequency with respect to that. So a PLL or a VCO, voltage controlled oscillator, or a PLL which in which the VCO is the integral part, is suitable for frequency demodulation. So the correct answer is FM signals. It is used for demodulating FM signals. So next, what is the bandwidth occupying 98% power as per Carson's rule for the following signal? Okay, so bandwidth occupies 98% of the power. So as per Carson's rule for the following FM signal. So here bandwidth is 2 times delta F plus Fm. So here the bandwidth will be 2 pi into 2 into delta F plus Fm. So what is delta F? Delta F is 4 into 10 to the power 4 kp am Fm. So kp am is 4 and Fm is 10 to the power 4. So kp am Fm will be 4 into 10 to the power 4. So basically a 4-year old and he is needing to go to his 4 what is so here 4 into so the Fm is 2 pi into 10 to the power 4 and Fc is 2 pi into Fc is 10 to the power 6. So we don't need Fc, we need delta F. So with delta F is kpam Fm. So delta F is kpam Fm. Delta F is kpam Fm. kpam is given to be 4 and Fm is 10 to the power 4. So delta F is 4 into 10 to the power 4. And Fm is 10 to the power 4. So the bandwidth is 2 into 4 into 10 to the power 4 plus 10 to the power 4. So it is 2 into 5 into 10 to the power 4 or 10 into 10 to the power 4. So this is 100 kilohertz. So the bandwidth is 100 kilohertz. Next, the modulating frequency in frequency modulation is increased from 10 to 20 kilohertz. So the bandwidth will be, as per Carson's rule, the bandwidth is directly proportional to Fm. So if Fm is doubled, the bandwidth will be doubled. The frequency deviation produced in a VHF carrier signal of 100 Hz is 50 kHz. The frequency of the modulation index is the frequency modulation index is the frequency deviation is 100 Hz is 50 kilohertz. So Fm is 100 Hz and delta F is 50 kilohertz. So with a 100 Hz message signal, you are producing 150 kilohertz of deviation. So the delta F is given to be 50 kilohertz and Fm. So delta F is 50 kilohertz and Fm is increase by 20 hertz. Next, the frequency deviation produced is the frequency. Acha. Here the 100 kilohertz signal is generating deviation of 50 kilohertz. So a 100 hertz signal is generating a deviation of 50 kilohertz. A 100 hertz signal is generating a deviation of 50 kilohertz. So the beta or modulation index delta f by fm is 50k by 100 or 500. So beta is 500. Correct answer is 500. The frequency curve is asymptotic. This is not important. Now compute the average transmitted power of frequency modulated wave with carrier signal cos 2 pi into 1000 t. Uh, so the power does not depend on frequency. So if the carrier is cos 2 pi into 1000 t, that is the carrier has an amplitude of 1. So a square by 2. So amplitude will simply be a square by 2. So it is power is simply a square by 2 if amplitude is a. So power is simply a square by 2 no matter what the status of the FM is, as FM only changes the frequency. So the power remains half. In next question, in a frequency modulation system, the maximum frequency deviation allowed is 1000 Hz and the modulating frequency is 1 kHz. So the delta F is 1000 Hz and FM is 1 kHz. So delta F is 1000 Hz or 1 kHz. So the max delta F is 1000 Hz and FM is 1 kilohertz. So the modulation index is simply the ratio of these two. So the beta will be delta F by FM. So it is 1 because both of them 1000 Hz means 1 kilohertz. So both of them is same. So it is 1. The modulation index is 1. Next, which of the following is used in this demodulating FM wave? So in a demodulating FM wave, so next question is which of the following method is used for demodulating FM wave? So to demodulate FM wave, we use the phase discrimination method, which uses voltage control oscillator. So or differentiator. Anyways, so we use the phase discrimination method. So here we use the phase discrimination method. With that, we will finish today's lecture. on FM, and next week we will be back with more. And in the meantime, take care. Thank you. So. Okay, one question we have missed, which is true in a frequency modulated system. So, in a frequency modulated system, A, variation of carrier amplitude does not affect quality of reception. B, amplitude of carrier is varied according to modulating signal. So, amplitude is not varied, so we can rule out option 2. Next, variation of carrier amplitude does not affect quality of reception, which is true because carrier amplitude has nothing to do with frequency modulation. Next, the transmission does not require line of sight between transmitter and receiver, whereas on the other hand, FM is very sensitive and FM needs strong line of sight for good reception. And receiver uses diode detector. So diode detector is basically an envelope detector, and the envelope detector is used in the phase discrimination method of phase modulation. So it is true that it uses some kind of diode detector. So the only correct answer is this one. Variation of carrier amplitude does not affect the quality of reception. Okay, thank you.